So we'll continue talking about predictive models. And you remember predictive models in its most general form is just a function that transforms inputs to the outputs. So we have some function f, which we call a model. And it takes some inputs x and generates some outputs y. And so far we talked about a linear model. So when this function f was a linear function, so for the linear regression case, linear model, this function f of x was just some linear function of the elements of this vector of x plus the intercept. So we have beta 0 plus beta 1 x1 all the way to x beta p x p. And we saw a lot of the applications for this model. So we did the housing pricing, we did the marketing example, and there are different types of this function f that can be used for the predictions. And today we're going to be talking about a specific version of this function f, a specific version of the predictive problem, which is called classification. Classification is the problem when we try to predict value y, which is categorical or qualitative, meaning that it takes some small number of possible values. The simplest case is 0, 1, which is called binary classification. So binary classification is y equals to 0 or 1, or yes or no, or disease, no disease. So it just takes two possible values, regardless of how you name them. It's just the number of the possible values that's important. Okay, and so for the binary case, when y takes just two possible values, 0 or 1, essentially what we are trying to predict, instead of predicting 0 or 1, we are trying to predict probability that y equals to 1 given x. So that's how we read the statement. This and you saw this in the condition when we talked about conditional probability. This bar stays for given, meaning that what we have on the right of the bar is given to us. We know the value of the x, and what we have on the left is the probability we calculate. So we calculate probability y equals to 1 given x equals to x, and as usual we have p predictors that we are trying to condition on and generate the prediction. So logistics regression has a lot of the uses, probably as many as your standard linear regression, where y takes specific possible values. And you can think of situations when you try to model win or lose, sick or healthy, medical diagnostics, buy or not to buy, when you try to predict the behavior of your users when they come to your website, pay or default, so if you're a bank and you try to predict the outcome for each of your accounts. And the goal essentially is to predict the probability that y equals to 1. And then we can use classification to categorize a new data point. So once you build a model that is trained on the recently observed examples, for example, if you're a bank, you train your default model on the previously observed defaults, and then a new customer comes in, fills in the application. So let's do a quick example. So y equals 0, meaning no default, and 1 meaning default. Okay, and x are the attributes of the customer, which comes from application form. So when you fill in the application form for the loan, you tell your gender, your age, your income level, your house ownership, your assets, and then bank will also get the credit history given your social security number, and it will combine all of those things. That will become the predictive variable x. So all of those financial and personal attributes from your application of your credit history becomes a big long vector, and then bank takes it and tries to predict whether this account, that if they are to open an account for you, whether you're going to default or not. More specifically, they're interested in the probability of you're going default given the personal characteristics, and then usually banks will put some threshold. So they say if the probability of defaulting is greater or equal than 0.2, then they reject the application, and if it's less or equal than 2, of course they will accept the application and you get the loan. So that's how this works nowadays. It's more or less an automated process with very little human interventions. Okay, so let's look at more specific example. Let's look at the default data. So again, why is default no default? And we're just going to look at the very simplified version of the predictive model for the default. X is going to be the average balance that customer has remaining on their credit card after taking their monthly payment. So it's basically how much of obligations the customer already has. Okay. And of course, you can, again, X can be a much longer vector of observations about the customer, but just for the sake of the demonstration, we're going to use this simple characteristic. Now we're going to use logistic regression. Logistic regression is a regression that uses this solves this classification problem, y is 0, 1. We're going to do the binary example here. And we need to model that probability y equals to 1 given the predictors. So what we need here, we need to let's start with that. So if we write something like this, y equals beta 0 plus beta 1 x1 plus beta 2 x2 all the way beta p x p. So if we try to write a model like that, that's not really gonna work. So one problem with this model is that what you have here on the right hand side, so this part, it can take any values from minus infinity to infinity. So any large negative number, so any large positive number, so 0. So it doesn't really help us to interpret the output of this linear equation. If we try to understand what's the probability, then we know that probability has to be between 0 and 1. So the trick is to do what is called the transformation. So instead of just writing model like this, we're going to introduce this intermediate value. We're going to call it p, and we're going to write it's beta 0 plus beta 1 x1 plus all the way to. So we're going to take this now, which we're going to call p now. That's going to be our intermediate value. And then what we're going to do, we're going to calculate the following function. Here I use x, but I'm going to calculate, so e to the power p, 1 plus e to the power p. So what this function does, and this is called a logit function or logistic function, that's why we call it logistic regression, so logit function. And logit function maps any number to a number that's in the interval 0 and 1. And that's exactly what we need. We need a number that lies in this interval between 0 and 1. So essentially, logistic regression is a two-step process. So first thing, we have to calculate this p, which gives us any number between minus infinity and infinity. And then we plug in p, we apply this logit transformation to it, and we get a number which is between 0 and 1. So that's it. We just added one extra step to the modeling process when we apply this logit transformation. Okay. Another way you can think about this, you remember that, so we have this value p, which is just a linear combination of the predictors, okay? And you remember that y equals exponent of power p 1 plus exponent to power p. And what we can do some simple algebra here. And this is equals, so our y, remember, it's probability that y equals to 1 given x. And we actually can do some simple algebra here, and we can invert the logistic function, and we can see that we can have a p on the right hand side, and on the left hand side we're going to have a logarithm of y divided by 1 minus y. Okay, so from here to here is just simple algebra that we're not going to do here. Okay. So now it gives a slightly different interpretation. It tells us that this value p, which is just a linear combination of the predictors, is the log odds. So odds is just, you remember that odds is probability of something happening. So in our case, we're interested in probability y equal to 1 given x, divided by 1 minus probability of this not happening. Also 1 minus probability of this happening, or probability of not happening. In other words, so probability of y equals to 1 given x. So this is the odds. And now if we apply the log transformation, we're going to get the log odds. So odds on the logarithmic scale. So p essentially, this linear combination, is the odds on logarithmic scale. That's all it is. Okay, and in R, it's easy to build those models. Instead of LM, we're going to use the GLM command, which stands for Generalized Linear Model. Generalized means that we take this linear component here, and then we generalize it by adding an additional function on top of it. So some function that maps it to a value between 0 and 1, so generalized linear model. Syntax inside the formula is the same, so we regress y on x1 and x2, but now we have to specify the binomial, meaning that values of y can be only 0 or 1. Okay, so G stands for generalized, GLM is the generalized linear model, which has many other options, but those are pretty much all you need. So let's look at an example. We're going to look at the NBA spreads. So the data set contains two rows, two columns. Column Y, which is the favorite or not favorite, and the column X, which is the spread. Okay, so that's our Y, and that's our X. So the favorite is either 0 or 1, and the spread is the spread predicted by the bookie. So how far away one team is going to be from the other. So that's the prediction by bookmaker. Okay, and now what we are trying to see how well bookmakers can do those predictions. So first we start by doing two histograms. So we're gonna take all the rows where favorite win was 0. So the favorite team did not win. And we're gonna look at, so you see this purple part of the histogram here. So that's the distribution of the spread that was predicted by the bookies. So you can see that actually for some of the upset situations, when bookies mispredicted, the spread they predict was all the way up to 20. But most of the times they will predict something that is close to 0. So it looks like bookies did relatively good job. Whenever there was an upset, the spread was relatively small. So when bookies put a small spread, they show that they're really uncertain about the outcome of the game. And now the second histogram is the purple histogram. It's the histogram for all of the rows where favorite team indeed win. And you see that, so a couple of observations. So sometimes the spread was all the way up to 40. So bookies was so confident that the team win, they will give those huge spreads. And also most of the times they will give the spread at around 5 here. So this looks like the highest value here. So bookies were much more confident. In those situations, it looks like they were this confidence was well justified. In fact, their predictions were correct in most of the cases. And let's look at the box plots. So again, you see the purple is for the cases when bookies did the correct prediction, and the purple ones then when bookies made the incorrect prediction. And you see the spreads for the incorrect predictions are much close to 0 on the median, and they're very close to somewhere, I guess, looks like somewhere around 8 for the cases when they did do the correct prediction. So just by looking at the plots, looks like bookies do make good predictions. The outcomes of the game actually confirm their confidence in the spreads. But let's check this by using the logistic regression. So we try to predict y. So we predict probability y equals to 1 given x. And y equals to 1 means that favorite team wins the game. So bookies did the correct prediction, and x basically tells the spread that was set by the bookies for this specific match. Okay. So we're gonna use this GLM command, and we regress the favorite win, which is a 0, 1 variable, to the spread column. And here we say -1. -1 means we do not want to use, so -1 means beta 0 just set to 0. So in other words, we do not use this beta 0 parameter of the model. Don't need to estimate it. And let's see what we get. So we just get one parameter that comes from a model, this beta 1, which is 0.15. So in other words, what we have is the log odds, or which is probability that the bookies did the correct prediction given x, divided by the probability that bookies did incorrect prediction given x. So if we take this on the logarithmic scale, it equals to 0.15 times the spread. Okay. So in other words, what happens if spread goes up? The odds on the logarithmic scale go up by 0.15. So log odds go up. So spread goes up by 1, log odds go up by 0.15. So essentially, model did confirm our exploratory analysis, our visual analysis, that bookies do a decent job when they try to predict the outcome of the games. So whenever they give a high spread to the team, then the log odds of this team winning actually go up. So the beta 1 is positive. Let's look at this model now. So you remember that probability of y equals to 1, in our case y equals 1 means favorite team wins the game, given the spread, is like logistic function applied to the linear combination of x's. So we just have 1x, we don't have beta 0, so logistic function becomes exponential to the power beta x divided by 1 plus exponential to the power beta x. So one thing we should expect if x equals to 0, meaning that the spread is 0, then the prediction from the model is going to be exponential to the power 0, which is 1, divided by the exponential to the power 0, which is 1 again, plus 1 times 2, so 1/2. So when spread is 0, meaning that bookies don't have any good idea about who's going to win the game, then the probability of favorite team winning is 1/2. Makes sense. So this is very logical. And now let's try to do the prediction. So if we try to prediction for the case when spread equals to 8, so remember our beta was what, 0.15? Yeah, 0.15. So when x equals to 8, the probability that the favorite team will win going to be exponent 0.15 to the times 8 divided by 1 plus the same number, exponent 0.15 times 8. So let's go to R and calculate this value. So we're gonna have exponent 0.15 times 8 plus 1 divided by 1 plus the same thing. So we get 0.76, 0.77 if we round it. So we get 0.77. So in other words, our model tells us when bookies put the spread of 8, meaning that they think that the favorite team will win by 8, it is equivalent to the bookies saying we're 77% confident that the favorite team will win the game. So we can go between the spreads and percentages using this logistic regression model.